Thank you. And well, thank you, Tiffany, for inviting me and for giving me the opportunity to talk here. It's a great pleasure. And yeah, as you mentioned, I want to talk about this project on emergent equivariance in deep ensembles, which I did with my collaborator, Pan Kessel, who is at Prescient Design in Switzerland. And before I launch into the main part of the talk, I want to give you a little, let's say, summary or a little sort of overview of what the main question is going to be and how I'm going to address this. And so one aspect of this project is in equivariant neural networks or geometric deep learning, which is this field that has really received a lot of attention over the last few years. And here the question is to consider symmetric learning problems. And so as many of you are probably aware, the general setup is that you have some symmetry group G that acts with some representation rho x on the inputs and with some potentially different representation rho y on the outputs. And then I want to call the learning problem symmetric if for each pair of inputs and outputs in my data set, x, y, and d, I know that the entire symmetry orbit, so rho x acting on x and rho y acting on y for all g and g, is also in the data set. And what this means is that the map from inputs to outputs that I want to learn has to satisfy this constraint. So namely, if I apply f to these transformed inputs here, I want to obtain these transformed outputs, and y I can of course write it as f of x. So that means my model has to satisfy this constraint, and if this output representation is trivial, then we call such a function invariant, and otherwise we call it equivariant. And sort of a very simple practical example of such a learning problem would be that we take here an image of blood cells in which the red blood cells are to be marked, that are these crosses here. And in this case, of course, if I rotate that image, then the crosses should rotate with the blood cells, and it will still, in particular, be a good sample of this data set. So here you would want to learn this sort of equivariant function. So in such a scenario, how would we go about learning? And one particularly simple approach that many practitioners like is to use data augmentation. And in data augmentation, what we do is that we train on some enlarged data set. So we consider our original data set, and then we just add the symmetry orbits of our elements to this data set. And note that here I'm taking this union over the group. So for a continuous group, this will formally be infinite. And then it means that people typically just sample from the group and they don't really augment with the entire group. So for my example of blood cells, what this would mean is that I do not only train on this version of the sample, but also on the rotated versions of the sample. And so let's think for a second about the advantages and disadvantages of this approach. And so on the one hand, it's very straightforward to implement. You don't need sort of complicated, adapted model architectures. But on the other hand, and it also works with any model architecture and any sort of symmetry that you can easily apply to your samples, and you don't need equivariant models for that. On the other hand, this does not yield an exactly equivariant model because, of course, we have to learn the equivariance and it will only be approximate. Then secondly, it will also increase the training time because we have increased the training data set. And this means that we have a particularly long training for continuous symmetry groups. So in summary, maybe we can say that it's good if the equivariance is not required exactly, or the group action is complicated, so that I might struggle to find an equivariant architecture. But on the other hand, it's not suitable if my symmetry needs to be exact. So for example, in many science applications. And so now in this project, the goal was to investigate this data augmentation theoretically, and to answer the question of what are the symmetry properties of neural networks that are trained with data augmentation. And the strategy that we want to apply here are to consider infinitely wide neural networks. So since we don't have a general theory of deep learning, we need to make some approximations. And what we want to do here is that we take this infinite width limit. And why is that helpful? Well, it turns out that in this limit, the mean output after some training time can be computed analytically. And I just want to give you here a hint. I will explain this in more detail in the next section of the talk. But the general idea is that I can compute this mean output on any test point at training time t with this expression, and it involves this neural tangent kernel. It involves the training data, the learning rate, and the training label. So sort of all the ingredients that you would expect that you need to compute the test output. And in particular, it involves this training data explicitly, right? And here, these capital X's. And what that means is that we can argue explicitly about training with augmented data, right? We can just plug in an augmented data set at these points and also augmented labels. And then what we can do is we can compute the mean output of a transformed sample. So we just add this row of G here and correspondingly here. And in this way, we get a handle on predicting how our neural network will behave under data augmentation. So let's now think about what sort of statement I can hope to get from this analysis. And for that, I want to say a little bit more about this mean function already at this point. And the way to think about this mu is to say that I take a neural network, I train it to time t, and then I evaluate it on my test sample. And then I do this, and then I take the expectation of this over initializations, right? So this will be a random variable in the initializations. That is what my mu is. And of course, I can write this expectation value here as the limit n to infinity of a sample mean with n samples by the law of large numbers. But this sample mean here just is the mean prediction of a deep ensemble. And this is why with this analysis, we will obtain a statement about an ensemble of infinitely many networks in the infinite width limit. And this is sort of why in my title I was talking about deep ensembles. Okay, so this is the general setup of the talk. And now I want to delve a little bit more into detail on the background. So on these neural tangent kernels and the wide neural networks, why we obtain the simplified version of the prediction. And to start with, let's consider an MLP. So a fully connected network, and we usually parameterize it in the following way. So we have some pre-activations that are just a linear function applied to the activations. And the activations are a nonlinear function applied component-wise to the pre-activations of the previous layer. And then we have our weight matrices in some input and output number of channels, and we sample the components of the weight matrices from a zero mean Gaussian, where the variance is 1 over the number of input channels, sometimes also called the fan-in. And so if you now investigate the scaling of the gradients of your neural network with respect to the components of the weight matrices, then with some simplifying assumptions like independence of the layers and so on, you can see that they scale in the following way in n. So if in the last layer they're constant in n, and in all the previous layers they scale like 1 over square root n. And here n is this sort of width of the hidden layers. And this is not optimal for considering the infinite width limit, because this scaling here will, or this update here will not decay to 0, and it will sort of induce a very complicated dynamic. And for this reason, I want to use this modification of the standard parameterization called the NTK parameterization. And here what happens is that, so this is what we had before, and now I want to add a factor 1 over square root NL minus 1 here in front of the weight matrix, and then in turn I sample the weight matrix from a Gaussian with variance 1. So this means in particular that the output distribution at initialization is the same, right? So this random variable here will have the same distribution as this random variable here. However, the gradients will scale differently, because now I take derivatives with respect to this w, and that means that I have to multiply by this additional factor of 1 over n. And we can see that in the gradient scaling. So now we have 1 over square root n for the first and the last layer, and then for all layers in between, we have a scaling of 1 over n. And so that means that in this parameterizations, the gradients vanish as n goes to infinity. And this then will make the dynamics tractable. And so we will use this NTK parameterization in the rest of the talk. Okay, so now that we have set up our neural network, we can think about how it behaves at initialization. And for a long time, so this first was worked out in the 90s, we know that neural networks at initialization in the infinite width limit behave as Gaussian processes. So to say this more formally, when we take the layer width of the neural networks to infinity sequentially, then the pre-activations at initialization become a Gaussian process with mean 0. So how you should think about this is in the following way. The pre-activations at initialization will be random variables depending on the exact initialization I have chosen or I have sampled. And these random variables will depend on the input and on the channel. And so it's a stochastic process. And now the statement is that this stochastic process is a Gaussian process with mean 0. And of course, a Gaussian process is not only characterized by a mean function, but also by a covariance function. And the covariance function of this Gaussian process has this structure. So it's some function depending on the two inputs, and then it's proportional to the identity in these channel directions. And so this means that all the channels are independent from each other in the infinite width limit. And this is then also known as the NNGP kernel. And this kernel can be computed recursively layer by layer. So there are recursive relations that tell you how to compute this kernel explicitly for different kinds of layers, like fully connected layers, convolutional layers, attention layers, dropout layers, and so on. So that means we can compute this thing in practice. So before moving on, I want to shed a little bit of a light onto why this happens. So let's consider the mean of the pre-activations. And so this mean will be an expectation value in layer L over all the weights of all the previous layers. And as we saw on the previous slide, in my parameterization, I have 1 over square root NL minus 1. And then this ZL is given by the weight matrix times the activations from the previous layer. And but now these activations, at least at initialization, will not depend on the weights in the Lth layer, which means that I can factorize them out. And then this expectation value here is 0 because we initialize the weights from a mean zero distribution. And similarly, we can now understand why the pre-activations become a Gaussian process. And this is just due to the central limit theorem, right? So if I, again, write the layer L pre-activations, then I can write this factor 1 over square root n as square root n times 1 over n. And then here I have the sum that comes from this matrix vector product here. But this combination here is just a mean over NL samples. And from an inductive argument, I know that these components are IID for different J. So that means all the conditions for the central limit theorem are satisfied. And I know that as I send this NL to infinity, this random variable will be distributed according to a normal distribution. And that normal distribution has mean 0, as we just verified. And well, this is the vector valued version of the central limit theorem. So there is some covariance matrix here. And computing this covariance matrix then essentially amounts to computing this NNGP kernel. Okay, so at this stage, we have a good understanding of the output distribution at initialization. But of course, what we are really interested in is training. So let's consider training. And here I want to make a slight simplification. So this is not fundamental, but it makes the algebra a little bit simpler. And that is to consider continuous gradient descent. So that means I want that the derivative of my weights with respect to time, so this would be training time, equals minus some learning rate times the derivative of the loss with respect to that weight. And the loss I want to write as an average over some sample loss, little l, between the outputs of the network and my labels. And now with 1 or 2 lines of algebra, you can convince yourself that under these conditions, the derivative of the output of the neural network on a test sample with respect to training time is given by this contraction here. So we have 2 derivatives of the neural network with respect to its parameters. Then we sum over all trainable parameters. We evaluate here this at the test point and at training points. And then we contract this here with the sum over samples into the derivative of our loss. And so you see that the thing that really drives this dynamics and characterizes our neural network is this term in red here. And this term is called the empirical neural tangent kernel, or empirical NTK. And in general, it's given by this expression. So it's theta ij for the different channels here of 2 inputs. And then we have this contraction of the derivatives. And to remind ourselves that this, of course, depends on the parameters of my neural network, I put a little theta here in the superscript. So let's now consider this empirical NTK at initialization in the infinite width limit. So, and there is this remarkable result from this paper by Jacot et al., where they found that this neural tangent kernel becomes deterministic in the infinite width limit. So when we take the layer width to infinity sequentially, then this empirical NTK at initialization converges in probability to a deterministic kernel. And so this is quite remarkable, because it means that sort of all these complicated derivatives of the neural network with respect to the parameters that we saw before collapses or conspires so that in the infinite width limit, it gives you a deterministic number. And how you can think about this is that essentially you have these 1 over n terms, and you have sums from the matrix vector product, and that will then give you, by the law of large numbers, expectation values, which are deterministic. And this deterministic kernel is then again given in terms of recursions over layers. So you can give a very explicit prescription for how to compute it. And for most common architectures, this recursion can then be performed explicitly. And there is even this Python package, neural tangents, that allows you to compute them. So you just put in a neural network in JAX, and then it will compute this kernel for you. Okay, so now we understand our NTK at initialization, but the hope was to really talk about training. And there comes maybe the most important result from this Gerken paper, and it is that this NTK features this freezing behavior. So what it means is that it will, in the infinite width limit, not change during training. And so explicitly, for some conditions on the nonlinearity, like it has to be Lipschitz, twice differentiable, and have bounded second derivative, this empirical NTK converges to this deterministic NTK at initialization uniformly for all training times as the layer would go to infinity sequentially. And so this is a very powerful result, because it means that now I can characterize my training dynamics completely by this NTK at initialization, which I have control over. So intuitively, this happens because we are in this NTK parameterization that I mentioned. And in that parameterization, the weight updates vanish in the limit n to infinity. However, now you might be worried, okay, if all the weight updates vanish, then does my neural network actually learn anything, or has the training completely collapsed? And as we will see, the neural network still does learn. And the reason is that although the updates of the individual layers go to 0, there are now also infinitely many of them. And then there is a non-zero collective effect. And I also want to mention that we now had a few times this constraint of going to infinity sequentially, but this is not a fundamental constraint. So there are now some other versions of these theorems that also work if, for example, you just take the smallest width to infinity or things like that, or all of them at the same time. Okay, so with this understanding, let's go back to our gradient descent dynamics, and let's consider in particular this continuous gradient descent we had before, but now for the case of the mean squared error loss. And so in that case, I have plugged in here the derivative of the MSE loss, and here we have the empirical NTK. But now, as we take the width to infinity, this empirical NTK freezes, which means that it becomes independent of time, and we just have this constant sitting here. And now this is an ODE that is tractable, and as you can guess, the solution is given by an exponential, and I can express the solution or the initial in terms of the initial conditions by specifying how the network behaves at initialization. So we get this this expression here where I have introduced some common notation. So capital X now is the design matrix, meaning that the row I of this matrix is the input I, and Y is the matrix of label, or the vector of labels. And this theta capital X, with that I mean the gram matrix. So the ij component of that matrix is theta applied to xi and xj. Okay, so now we have obtained quite a powerful result, right? So given the initialization, we can predict the training dynamics of this neural network for arbitrary test points explicitly. But we can now consider the statistics of this, because this is, again, still a random variable because it depends on the random initialization. But we established before that these random initializations, they are Gaussian processes. So, and this here in black is just a complicated matrix, meaning that what we have done is we have taken some linear combination of Gaussian processes. And as such, the result is, again, a Gaussian process. And so we can now go ahead and compute the mean function of this Gaussian process. And this is very straightforward because we said that the mean of this f at initialization is 0, meaning that we just drop this term and this term, and we arrive at this result for the mean function. And similarly, you can compute the covariance function. And the covariance function is given by a longer expression like this, but you can still compute it explicitly. So, and to illustrate what these behave like, you can consider training samples. You can consider what this mean function and covariance function behaves as t goes to infinity on training samples. And what you would hope, of course, is that on the training samples, you, at infinite training time, get the training labels back. And this is exactly what happens, because this term here will drop away, and then these two terms will cancel, and you're just left with y. And similarly, you can also verify that the covariance function at infinite training time will be 0. Okay, so this is as much as I wanted to say about the background on neurotangent kernels and infinite width. And with this technology now at our hands, I want to consider data augmentation and then investigate what the sort of transformation properties of the neural network will be. So let's consider data augmentation in this context. So we assume that we act with representation rho x and rho y of some symmetry group G on the samples and labels, like this. And then what we want to do is we want to augment our training data set by these full group orbits of the training samples, yielding an augmented data set like this. So again, I want to use the capital X and capital Y to denote the design matrix and the labels of this augmented data set. And I will just join the entire orbit of the training samples of my original data set into this. And of course, for this, I need to consider a finite group so that this is still a finite size training data set. But I will comment on continuous groups in the end of the talk. So let's now consider a finite group. And then what this means is that if I transform a training sample, then this is equivalent to permuting the training samples, right? So since I have all the entire symmetry orbit in my new augmented data set, if I just transform one, I will just select a different training sample, and I can describe that with this permutation pi. And of course, the same is true for the labels. And so we can now use this to act on all the training samples. And then what this will do is it will induce a permutation matrix on this design matrix. And so, for example, if we consider the NTK evaluated on rotated training samples, this sort of gram matrix, then it means that I just act with a permutation matrix on the rows and the columns of my gram matrix. Okay, so this is how we will treat data augmentation in this context. And now I want to extend this and think about general kernel transformations. So I have a transformation of the inputs, and this will induce transformations of the kernels as well, like this, by just acting on both slots. And note that here, these are not training samples. These are just arbitrary points at which I choose to evaluate my kernels. And now we worked out how these kernels transform under such a transformation. And what we found is that the NTK and the NNGP transform according to this law. So it's they are almost invariant, but you have to multiply with this rho k and rho k transpose. And these rho k's are a transformation that act on the spatial dimensions of the kernels. So this is something I haven't mentioned so far. If you have an output of your neural network, an output dimension that you don't take to infinity and this infinite width kernel limit, then the kernel will have an additional index corresponding to that dimension. So think about a network that outputs an image, for example, in a CNN, then typically you wouldn't take the pixel direction or the spatial directions of your neural network of the CNN layers to infinity, but you would take the channels to infinity. And then the NTK of this network would still have these spatial directions, so these pixel positions. And so if the kernel does not have such spatial axes, then these rho k are just the identity. So this is, for example, the case of MLPs that we have considered before. And at this point, I want to briefly sketch how we went about proving this. So we did it inductively over layers using these recursion relations that I alluded to before. And we did this for nonlinearities, CNNs, fully connected layers, and flattening layers, so that we could build sort of a simple, or could fully cover a simple CNN classifier. But this can also easily be extended to many other layer types, like, as I mentioned, dropout or attention layers. And I will comment on this in the end again. So as an example, let's consider the induction step for the NNGP of a CNN layer. And so for that, we need to make an induction assumption. And the assumption is that on the previous, the L-1 layer, the kernel has this desired transformation property, which is that if I act here on X and here on X prime, then it's the same as if I act on these spatial directions. So A and A prime are these pixel positions that I mentioned. And here I will act with rho inverse G and rho inverse G on both of them. So this corresponds to what I called rho K and rho K transpose before. So let's now see what happens for the layer L kernel. And well, what happens is that we act here, and we first use the recursion relation, which is just given by this here. So I take the previous layer's kernel, and then I sum over A tilde and add A tilde here to A and A prime. And there is only one sum, and it's the same A tilde. And then I can use my induction assumption. So that moves the rho x, it removes the rho x here, and it produces the rho inverse G here. So this comes from this induction assumption. But now, of course, I can redefine my summation variable and absorb this rho inverse G. And then I have something where, again, just sum an A tilde. So it means now I have KL of rho inverse G acting on A and A prime. And this is, as I said before, just what I mean by rho K and rho K transpose acting. And then in a similar way, we have proven this for all the other cases that I mentioned. So with this kernel invariance, let's first consider it in a slightly different form. So here we apply, this was the form that we had for our kernel invariance before. And now what we do is that we send X prime to rho inverse G X prime to move it here to the right. And we want to do that because now we can, if we combine that with data augmentation, we can argue about this permutation matrix. So here I consider this permutation matrix that is valid on my training data set, and I permute the rows of my gram matrix of the neural tangent kernel. And first, by the definition of this permutation, I can just move this or replace this permutation by a transformation on the training samples. And then by this version of the kernel invariance, I can move this kernel invariance over to the right, paying with an inverse, and then I get a pi inverse transpose, which becomes a permutation from the right. So we see that we can just commute the permutation past theta, past this gram matrix. And actually, this statement is true much more generally. So we proved that this data augmentation implies that you can permute this commutation matrix through any matrix-valued analytical function that involves the gram matrices of the NNGP and the NTK, as well as its inverses. And the price you have to pay is, in general, that you have to consider this rho K matrix. So this didn't appear in the previous slide because there I considered MLPs again, where the rho K is trivial. And so let me just briefly sketch the proof here as well. So we proved this separately for theta, theta inverse, K, and K inverse, and all powers of these. And we considered, and here let's, for example, consider theta inverse. And then it's essentially a game of playing with inverses here, right? So we have here an implicit assumption over L, and then we say, okay, if I multiply this matrix by its inverse, I get the identity, and now I can replace this row here by a permutation, and then I can move the permutation over by redefining my summation variable. And of course, now I have uniqueness of the inverse, meaning that I know that whatever is written here will be the inverse of this if it results in the identity. So I know that the inverse of this is just given by this. This is this equation. And then I can again move this permutation over to the left by redefining the variable. And similarly, you can prove this related relation where the permutation sits on the other slot, and also the representation sits at the other slot. And if we put this together, then we can prove this permutation shifting for the inverse of the NTK as well. So we consider here the permutation acting from the left, and then this becomes a transformation acting on the right slot, which by this statement here, we can then make a permutation acting on the left slot. And now by, we do this here, and then we move it over, and there we get the rho K. So this is the kernel transformation. And then we use this, and so this gives us this right-hand side here. And note that I could pull out this rho K from this inverse, because the inverse acts on the sample indices, whereas this rho K acts on the spatial indices. So now we have learned a lot about how these gram matrices behave under data augmentation and transformations, and we can now put all of this together. So let's, as an example, consider again an MLP which is trained with data augmentation towards invariance. So that means we now consider the mean prediction in this scenario on a transformed test sample like this. And first of all, we get this row acting on X here. And now by the kernel transformation, we can move this here to the right. In an MLP, we don't get any row Ks. And then when it acts here on the training data, then this is just a permutation. And now this permutation, we said we can move past any analytic function in theta and its inverse. So we can just move it here to the right. until it acts on Y. But we assumed that we had trained towards invariance, and that means that this Y vector will be invariant under these permutations. And so the pi here just goes away. And that means that we just are left with this expression here, which is, of course, what we originally had for the mean prediction on a test sample. Okay. But this statement can be made much more general, and this is our main result from the paper, and namely that the entire distribution of the large width ensemble members, f theta from x to y, is equivariant with respect to the representation rho x and rho y of the group G if data augmentation is implied. So the entire distribution is equivariant, and this means in particular that the ensemble mean, which is this expectation value over initializations, is equivariant, meaning that if I act with my rho x on the input, it's the same as acting with rho y on the prediction. And so note that this holds in particular at any training time and for any element of the input space. We prove this, of course, by showing this equivariance for mu t, so for the mean function and the covariance function of this Gaussian process. And so note that this makes the result, these 2 points here make the result very non-trivial. Because you might believe that if I tell you, okay, you take an ensemble and then you train it with data augmentation, you know that ensembles work really well. So you can believe that it sort of approximates equivariance, and it becomes better if I take really many of them. But this will hold only after training, and on the train data, or maybe on the validation data as well, if your ensemble generalizes well. But this goes much further, and it says that this will happen at any training time and for any element of the input space. So in particular, also out of distribution. Now you might wonder what happens at training time 0. Then, of course, the ensemble can't know anything about the training data, and that is true, but then the mean prediction will be 0, and that is, of course, trivially equivariant. Okay, and so this we wanted to verify with some experiments. And the first experiment I want to discuss is the Ising model. So in this model, you consider a lattice with spins. So these are just variables that take on the values +1 and -1, and you compute the energy of the configuration in this way. So you take minus some coupling constant over the number of lattice sides, and then the sum I over the lattice of this local energy EI, and that is just the product of the spin at position I with all the neighboring spins and then summed up over neighbors. And now the task is to predict this energy given the spin configuration. And this problem has a C4 symmetry, so that means lattice rotations by 90 degrees, since this EI here is invariant, and then the total energy curly E is, sorry, it's equivariant, and then the total energy curly E is invariant. And on this, we trained a one hidden layer MLP on 128 samples, which we augmented by 4 because of this C4 symmetry to 512 samples. And then we trained that under the MSE loss on these energies here, and then we predicted the total energy by just summing up with full batch gradient descent. So in this scenario, we are very close to the scenario we considered in the theory. And for the system, the NKK can be computed exactly. So we did that with this neural tangents package. And we also considered out of distribution data by sampling spins from this Gaussian, centered Gaussian with variance 1. So let's first verify, or the first thing we did was to verify that actually we converge to the NTK. So what you see here is the relative difference to the NTK from our finite size networks. And here you have the ensemble size from 10 to the 2 to 10 to the 4. And we have three different widths, 512, 1024, and 2048. And we see that the relative difference goes to decreases as we consider wider neural networks. And this happens on the training data, on the test data, and also out of distribution. And what we furthermore see is that these lines are essentially flat in the ensemble size, meaning that we have sampled in our Monte Carlo estimate of the ensemble mean apparently already enough samples so that there is not a big fluctuation. But of course, what we are very interested in is the invariance behavior of this model or of this ensemble, and we want to measure it using this, what we call the relative orbit standard deviation. So the idea here is that we take the four rotated versions of the lattice, we predict the energy, we get four energy predictions, and then we take the standard deviation and we divide by the mean. So the idea being is that the standard deviation is of the same order as the mean, then there is essentially, and this measure is 1, then there is essentially no invariance being learned. And then if it's smaller than 1, then this model shows more equivariance, and a perfectly equivariant model would show 0. And here are our results. So here we plot the relative orbit standard deviation. And the solid lines here correspond to the ensemble members. So here we evaluated this metric for each ensemble member and then took the mean over ensemble members, and then plus minus the standard deviation for the bands. And you see that out of distribution, there is essentially no difference they're essentially not invariant. It's all compatible with 1. And you also see that they overlap quite a bit, these error bands, meaning that aside from this effect here, we don't really gain much invariance by making the network wider. But down below, you see these dashed lines, and these dashed lines correspond to evaluating this on the ensemble mean. And you see here that there is a clear gap. It's much more invariant. And even out of distribution, we find invariance for the means. And so you can zoom into that a bit more, into these dashed lines. And now you see that as predicted from theory, the invariance becomes better if we increase the ensemble size, and it becomes better as we make the network wider. And this is true on the training test and also on the out of distribution data. Then we wanted to try this on a more realistic sample as well. So here we considered an ensemble of CNNs trained on Fashion MNIST, augmented now with not just 4 rotations, but also 8 and 16. And we measured invariance with the orbit same predictions. So the number of predictions in the orbit which agree with the prediction of the untransformed sample. And what we see is that throughout training, so here we plot this orbit same prediction over the training epoch, the ensemble predictions are more invariant than the predictions of the ensemble members. So these bands here are 25th to 75th percentile of this metric over ensemble members, and the solid lines are the ensemble predictions, and then the dashed lines would be perfect invariance. So this is for C16, C8, and C4. So also here we can verify the result. And with this model, we also investigated continuous symmetry. And so for this, we only expect approximate invariance, since we cannot augment with the entire group orbit. And we also expect that if we augment with more samples, then the invariance should increase. And we see this explicitly. So here we compute the fraction of the predictions that agree with the prediction on the untransformed sample. So 1 would correspond to perfect invariance, And we see that indeed, as we sample more during the augmentation, as we augment more, we get higher invariance. And there is, again, this gap between ensemble members and then the ensemble prediction. And finally, we also tried this on an equivariant task. What I presented so far were invariant tasks. So here we predicted the cross products. So you take two vectors in R3, and this is equivariant because under rotations, because if you rotate both vectors with the same rotation, then the output will also be rotated. And we again see here this big overlap in the ensemble members, but no overlap for the, but a much higher equivariance for the ensemble predictions. And this is also why we call this emergent equivariance, because the equivariance sort of emerges from the non-equivariant ensemble members. All right, and with that, I would like to conclude. So in summary, I said that under data augmentation, ensemble predictions become exactly equivariant in the large width limit. And this equivariance holds even out of distribution and at any training time. And we showed this explicitly by computing the transformation properties of the neural attention kernel under data augmentation. And if you're interested in applications, then I think there are two points of view that you can take. So one is that if you need for your application an ensemble, for example, because you need uncertainty estimation, then you can consider data augmentation instead of an ensemble of manifestly equivariant networks. And this data augmentation will work much better in the ensemble than for the individual ensemble members. On the other hand, if you need data augmentation, for example, because no manifestly equivariant model is available for the task that you're interested in or the symmetry you're interested in, then you can consider using an ensemble to boost the equivariance. And finally, let me give you an outlook. So it would be very interesting to extend the proofs to general layers. I mentioned before we had this handful of layers where we showed this explicitly, but we have some ideas and are currently working on a general argument that will work for larger classes of layers. Then I think this continuous approximation is worthy of further investigation because this is the really practically relevant example. And there are some interesting approaches in the literature where, for example, this is used with things like where people use Markov processes to sample sort of steps of various augmentations, which I think would be quite an interesting approach here. And finally, of course, we have considered in our theory only infinitely wide networks, and this is a restriction. And I think it would be interesting to consider finite width corrections. So there is now some literature on this. And of course, everything becomes much harder, but it would be interesting to see if you can say at least something about these corrections in the case of data augmentation. Well, and with that, I would like to thank you. Here is the reference to our paper, and I'm very happy to answer any questions.